Now we're going to try to compute this composition of this function. So we're going to compute f circle f by using this function f of x is x plus 1 over x minus 1. So first, let's compute this one without worrying about the domain of definition, because it's clear here that we're just using the restriction. So x should be different from 1, but here we are worried only on 1 plus infinity, so we don't have a problem of the domain of definition. Okay, for this first one, we will see if we have any problems later. So let's work on this one. By definition, we have f circle f of x is just f of x. So we go to any x in f and we plug f of x. So we have f of x plus 1 over f of x minus 1. So this is an easy way. Now what's f of x? So it's x plus 1 over x minus 1 plus 1 over x plus 1 over x minus 1 minus 1. We do the algebra, so we get x plus 1 plus x minus 1 over x minus 1. And here we have x plus 1 minus x plus 1 over x minus 1. So working everything out, we get 2x over x minus 1. So now we're going to flip x minus 1 over 2. That means since this one is not 0, this one is not 0, we can cancel, and we cancel by the 2, we get x. Okay, therefore f circle f of x is just x. Okay, so this one, let us compute something. It seems like f is its own inverse here in this case, because when we're dealing with inverses, we have f circle f of x is x with some conditions on the domains. Okay, so let's see what we can do here. So our function here, f here, is defined on this interval 1 plus infinity. It's decreasing. Okay, this function is decreasing. Yes, it's decreasing. We have to prove this result. Okay, the limit is 1, and we can rewrite it as, so let's see why this function is decreasing. F of x is x plus 1 over x minus 1. So it's good to simplify it. So add and subtract 1, so we get x minus 1 plus 2 over x minus 1, which is 1 plus 2 over x minus 1. So this is a constant, but this is decreasing. So therefore, it's a decreasing function. If you are not convinced, you can compute f of x is f of x less f of y. Okay, given that x is less than y, or f of x is bigger than f of y. Okay. So if it's decreasing, we will see that given x and y, so f of x is going to be bigger than f of y. That's what we need to have. Okay, and we see clearly that this one is true. So that means f is decreasing. If it's decreasing, so we're going to find the image of this interval 1 plus infinity by f. And once we do that, it's the same here. That means f is surjective. Okay, so the image of this one is the whole set. So that means every element in here get hit by some element from here. That means f is surjective. The only thing left is that we need to prove that f is injective. Okay, so let's do this. So f of x is f of y. We need to prove that x is equal to y. So using this expression, this means that 1 plus 2 over x minus 1 is equal to 1 plus 2 over y minus 1. So here, subtracting by 1 from both sides and dividing by 2, we get 1 over x minus 1 is equal to y minus 1. Okay, so multiplying, get y minus 1 is equal to x minus 1. That means y is equal to x. That means this means that f is injective. Therefore, f is both injective and surjective. Therefore, it's a bijection. So from here, we conclude that the f inverse of x is just itself. Okay? Because once we compose here by f, we get x, and here we get x. So that means the f inverse of our function is just itself. Okay? And this proves our result that we need to find f inverse. Okay? If you are not convinced that this is our f inverse, you can solve f inverse of x, f inverse of y is x, or you can, since you have the expression for x, you can solve f of x is y and switch back x and y. Okay, and that's the traditional way that we used to do. But here we don't need to compute this one because this is already enough. It's already convincing for us.